Okay, let's do an exercise. That is the same exercise you can find in the student paper RT-Script. That was an old examination task many years ago, which is three cascaded loops with three loops with three integrators. You see the process, original process, has three integrators. Note that each integrator has a fixed phase shift of -90, and with three in series connection you have a total phase shift of -270. With one single loop it is absolutely impossible to stabilize this system, because PID has a maximum of +90, ideally +90, and then you have a total phase shift of controller +90 and 3 times -90. So finally you have a negative phase shift of -180. There is no omega, no any frequency where the phase is more positive than -180. That means you cannot find any position where you have a positive phase margin. So with a single loop system, this three integrator system cannot be stabilized. But you see, very simple, with three P controllers, not PI, not PID, just simple P controllers with two additional internal negative feedbacks, you can solve this system. And here in this task you have three design informations which should be used in the next step. So we start with the internal loop. Here you can read the design the three-level cascaded control system. The internal loop should be designed in that way that the closed loop time constant with K3 is 5 seconds. So this should have a time constant. The closed loop system should have a time constant of 5 seconds. So we start now with the internal loop with an integrator of 3 per second. Exercise with an old examination. You can find also in our Moodle course, and the internal loop starts. This is a system with a P controller. The P controller has the name K3 and works with an integrator with a K of 3 per second and then a negative feedback. So this is the first step what we have to do. Internal closed loop should have a time constant of 5 seconds. So what we have to do is very similar to the project 1. Calculate the closed loop transfer function of this and look if we can then identify a time constant in this transfer function. So we start with FWI, which is open loop is K3 times 3 per second divided by P, coming from the integrator, divided by 1 plus, that is the closed loop system signal block diagram reduction equation, chapter 2, divided by the 1 plus open loop. And you see I multiply in both cases with P, so I have here a K3 times 3 per second divided by P plus K3 divided by 3 per second k3 times 3 per second. So, and you see constant in numerator is first order term in denominator. This is a PT1. The closed loop internal system behaves like a PT1. We have to normalize this, otherwise we cannot identify time constant. Normalizing means in a sum, in a polynomial function, the term without a p should be set to 1. So we have to divide by 3k3 over second. And you see in the numerator we have a 1, and in the denominator we have a 1 plus p divided by 1 second divided by k3 times 3. So this is the closed loop internal transfer function, and this is a PT1, and you see the coefficient in normalized function. If this is 1, the coefficient is an internal time constant, and the task says this internal time constant should be 5 seconds. So the result is then 5 seconds should be set equal to 1 second divided by k3 times 3, and we solve this for our unknown p controller gain k3. K3 is then 1 second divided by 15. This is then 0.667 seconds. Okay, not seconds, sorry, seconds, no seconds, of course. On both sides we have 1 second. Yeah, here we have 5 seconds, here 1 second. Second can be deleted. Of course, K3 has no unit. So the internal loop is closed. If we look on our system, we can say, okay, let's copy this picture and make some drawings in it. We can say K3 is now 0.0667, and this part here, this part is our FWI, which we have calculated here, so that we now can start for the middle loop. The middle loop needs the calculation of K2. K2 is a P controller. I just draw this in a new situation. This is K2. This is then a PT1. The closed loop FWE, we have just calculated some seconds before, is a PT1, and we have to add now the second integrator with our 5 second value, and then we have an internal negative feedback. So we have a middle loop with a PT1. The time constant here is 5 seconds coming from the task. Question is, how large is this K? There is a typical error I see very often in examinations. Then you assume that this K is K3. Don't do this, please. That is not K3, because the K of your PT1, the K of your PT1 is in the normalized function is the factor in the numerator. This, we can say, this can be called K, new K with W internal loop. That is the gain of the closed loop system of the here black dotted area, gain of FWE, and this is 1. Now very important, don't mix it up with K3. K3 is the open loop gain and 1 is the closed loop gain. That is the difference. Okay, the task of the middle loop. How large should K2 be? What is the task? We should open the task again. This is the copy of this. The middle loop here is choice of K2 such that damping D is 1. Flash control design is possible. How large is the resulting omega naught? So this is the design hint in the examination. I have told the students there that you can use a flash control design. The question is, what is this for a combination? It is a combination we know from flash design. So I think I open workbook page 33 and we look what this is for a combination. So this is page 33, flash design, and 33 contains 5 combinations, only one with a P controller. The I, PI, and PD, PID doesn't match. So the only thing is what we can see that this could be a P controller, but we need an IT1 process. Really, is this an IT1 process? Yes, you know the process transfer function process is a PT1, 1 divided by 1 plus P times 5 second multiplied with, oh sorry, this must be 5 per second. 5 per second is the frequency. The K of the integrator is the frequency. 5 per second divided by P. So the product is the total transfer function, and this of course is that what we call an IT1. This is the KI, and this is the time constant TI of the PT1. The IT1 transfer function is written in workbook in the following form. We have the P controller, this is our K2, and the process is a KI divided by P times 1 plus P T1. T1 here is our TI. So this is exactly our transfer function, and this is the design result. We just have to copy the design result of page 32. I copy it. Yeah, IT1 is KI divided by P1 plus PTI. Design result of workbook page 32.2.1 is the K2 is wrong page is 1 divided by 4 T1 D squared Ki. 1 divided by 4 T 1 T is our TI D squared times Ki. Again, control 4 T1 D squared Ki all in the denominator. In our case, which numbers we have? We have the 4, our TI is, the time constant is 5 seconds. The D is, according to the task, 1 squared. I write it so you know where this comes from. And Ki is our 5 per second. 5 per second, and you see the seconds again are eliminated. So we have a K2, a P controller again, which has no physical unit, and the result is 1 divided by 4 times 5 times 5 is 1 divided by 100. this is 0.01. K2 is then designed, and in the task also the radiant frequency, the natural radiant frequency of the closed loop PT2 behavior is asked, because we need it for the external loop. We look into our solution. You see, can be easily calculated by this equation. Omega naught is 1 divided by 2 dt1, 1 divided by 2 d times here ti, our ti. This is 1 divided by 2 times d times ti is 5 seconds. So we have an 0.1 per second value for the omega naught value. So this is the very quick design of our middle loop. So what do we have? We have calculated our K2, which is now 0.01. We have calculated the green loop. The middle loop is here, I should mark it, the green part. You can say is now solved. Let's call this FW2, according to our K2 here, FW2. And I have just quickly put all information together. FW2 is a PT2 with these given values, and now I draw the third external loop. We have our K1, our green area, our PT2, and added with our third integrator 7 per second as a process part, the third process part, and the closed loop system is then indicated with the third negative feedback here. So now the design of K1 should be done with the following text. Before we start here, note the hint here in the task is the middle closed loop can be converted into 2PT1. So can be converted, we should do this. If there is a hint, can be converted, of course, then I assume that you will do this in this task. How large are both time constants? This question should be solved. So we have convert PT2 into 2PT1s. Look into the workbook on the correct page. And then here the design message is, we have a P controller has only one parameter, the gain, and with one parameter we can only design a loop with one property, and the property here is use FRA design, but drawing is not necessary. We don't need to draw a Bode plot. How large are omega d? And this is an error here, of course. This should be K1. How large are omega d and K1 if the phase margin is 60 degrees. So here should be done FRA design with given phase margin. That's what we have to do. So first PT2 into 2 PT1s, and second K1 with phase margin is 60 degree. This is information from the task. And we want to do this, or should do this, with FRA without Bode plot. The Bode plot normally is necessary because this is the only information we have. Here we have more information. We have transfer functions. So we can use the idea of the FRA with the Nyquist equation, with both the phase and the magnitude Nyquist equation, and can check if we can solve this without drawing the Bode plot. Because this is an examination task, of course this should be possible. Yeah. First, PT2 into 2PT1 conversion. The PT2 pages in the workbook give the answer. Go to page 23. Here you see the conversion. using the parameters of a PT2, and then the K is the same, in our case 1, and T1 and T2 can be calculated with these both equations. T1, T2 is d plus or minus square root d squared minus 1. In our case is d1, so the square root is 0. So we have 1 divided by omega naught. And plus or minus 0 means T1 and T2 have the same size, the same value. So note in our book with Workbook, Page 20, was war das nochmal? Wieder vergessen. 23, T1, T2 is in the denominator our omega naught. Then we have d plus or minus square root d squared minus 1. Because the d is 1, square root is 0. Then we have 1 divided by omega naught, and this is 10 seconds. So we have two time constants with the same size, 10 seconds. So we have a new plan. Let's draw this new plan so that you can follow the next step. K1, then the converted PT2 into 2PT1. are now drawn with 2 blocks. The gain in both cases is 1. And here we have 10 seconds, here we have 10 seconds, and here we have our integrator with 7 per second. Negative feedback. So this is the situation in the design of my last K1, and now this is a loop where we have only design information. The phase margin should be 60 degrees. So we can say, okay, how can we solve this? Let's use the Nyquist equation. Nyquist equations. It's the base of our Bodeplot FRA design. One is phase margin is 180 plus open loop phase at omega d, and magnitude of the open loop at omega d should be 1. That is the knowledge of my stability criterion of Nyquist. We use these elements, so we need at first the information how large is the open loop phase. The open loop phase is a phase of all 4 blocks. P block has no phase, so we have 2 times PT1 phase and 1 time an integrator phase. So we know the open loop phase at omega d should be in both sides minus 180 gives minus 120 is 2 times the phase of an PT1 is negative arctangent omega d times 10 seconds minus 90 degree. The phase of an integrator is constant, frequency independent, 90 degree, and the phase of a PT1 is well known, is omega d times time constant of the negative arctangent value. So we see on all elements we have a negative sign, so we multiply this with minus 1, it's a complete equation. And you see now this can be solved to omega d, very simple, because that's the only element omega d in this equation. So on both sides minus 90 gives here plus 30. We divide by 2, and this is arctangent omega d times 10 seconds, and we solve this easily. Then omega d, the crossover frequency, is then tangent 15 divided by 10 seconds. tangent 15 degrees divided by 10 seconds, and this value gives, with handheld calculator, a very small value, 0.02679 per second. So the crossover frequency is now calculated, and now we can go into our magnitude equation, which should be 1, and we have the magnitude K1, magnitude of this, and the magnitude of 2 times PT1. This gives K divided by square root 1 plus omega d T1 squared. That's the magnitude of the first one. The magnitude of the second one is the same K, and you see with the same T1 we have simple expressions, and the magnitude of my integrator is 7 per second divided by omega d. So we can put these together. 2 times the square root function doubled is K1 times 7 per second divided by 1 plus omega d times 10 second squared divided by omega d. And if you put omega d, the calculated omega d, into this expression and solve for K1, then K1 gives the following result. And after some calculations, you get 0.004103. And then this task is completed. You see, I have solved this task within 27 minutes. That is just in this examination. I think the estimated time you have, just check how many points this task would have given. In the task you could get 30 points. 1 point is equivalent to 2.5 minutes time in examination. So these are 75 minutes, more than 1 hour time available for this task. I have solved this in 27 minutes, so you see you have more than 2.5 times more than I used to solve this equation, solve this examination task. Okay, note these old examinations have so many tasks for 3 hours. The examination time for 18 years ago was 3 hours. Today we have 2 hours, so you get less tasks, with, of course, in total less points. Yeah, note this is the last lecture video containing exercise task, video number 65. You can find more examinations, more exercise task in RT-Script. If you look into this paper, then you see this task is available, but then there are some other tasks. Okay, just a check. Yeah, we have, for example, cascaded loop Bay 46A3, then completely calculated then in old examination with a given electronic circuit where the equations are given, and you should set up a signal block diagram. This is one example of solution. Here you have a mechanical system with given equations, and you should set up the signal block diagram. Then you have here a task of reduction, given by 56, given signal block diagram, and you should calculate the overall x over w transfer function with the solution, a stability analysis with Hurwitz, with the you see this is an example where k has to be investigated if the stability range, and this is only possible by using investigating a second order parable function where the stability range is defined. The parable function with this zeros here at that point has to be calculated, and then we can say within this range this is stable, outside this range this is unstable. So the fourth order system finally has to be investigated with this inequality, and this inequality leads to a second order inequality equation which has to be investigated. In this task there should be calculated that is for a task, a Laplace transformation task. The output it should be calculated, the step response should be calculated in this task. You see many tasks up to page 116. I don't want to execute all these examination exercise tasks. I think you should try to solve these tasks for yourself, and then look into the results here in this paper, compare them. If there are differences, try to find the reason. Mostly mistakes in your calculation. I think with all these videos you should be able to prepare for the examination and the lab properly, and you have, I think, now time enough to do this. What you only get is 3 more videos, each video for preparation information for the 3 lab tasks. That's the last point today.